Okay, all right. So thank you so much for the introduction. And my name is Kun Zhang, and I'm an assistant professor from the Department of Civil Engineering at California State University, Chico. So today is my great pleasure to talk about my research of recycled olive pomace as a natural additive to improve the antioxidant performance of the asphalt paving materials. So first, I would like to acknowledge all the sponsors for this work, the California State University Agricultural Research Institute program, and also the grant from the Olive Oil Commission of the California, as well as the CSU Chico RSCA program, and also the APWA Sacramento chapter to sponsor the equipment used in this project. And also, I would like to acknowledge the partnership with California Olive Ranch, which is the largest olive oil producer in the United States, who provide the olive pomace used in this study, and also the UC Davis Olive Center, who help to test the residual oil content in the olive pomace. So a little bit background of the olive oil industry, which is one of the most important agricultural sectors in the Mediterranean areas, especially in European countries, for example, Spain, Italy, Greece. Well, in the United States, the state of California is the only state to plant olives, produce and export the olive oils. If we look at this chart from 2008 to 2017, the annual production of olives in the California increased from 66,000 tons to 192 tons, which means like the annual production increased by almost 200%. Well, the annual revenue from the olive oil industry increased from 46 million to 186.6 million in these 10 years. However, as more and more olive fruits were harvested and processed as olive oil, then in the olive oil industry, the waste management becomes a problem, because from the olive fruit to the olive oil, so only about 20 to 30% of ingredient from the olive fruit can be extracted as olive oil. Well, the rest of 70 to 80% are byproducts, which is called the olive pomace, which includes the moisture in the olive pomace, which includes the olive stone and also the olive skin, or we call it olive pulp. So annually, there are about 20 to 30 million tons of the olive pomace created globally, again, especially in the European countries, while in California, there are about 150,000 tons of olive pomace need to be disposed of or recycled. So you can see the stockpile of the olive pomace from the olive oil after the olive oil extraction. Well, there are some current recycling methods of using the olive pomace. For example, use it as animal feed. However, it may cause the anti-digestive problems of the cow. It may be used as a soil fertilizer, but the olive pomace is acid. So the pH is less than 7. So it may change the pH of the soil. So it may reduce the seed germination. It can be used in the cosmetics, while the processing is very expensive. So there's a need to find the way, the economical way to recycle the olive pomace. Well, we propose to use the olive pomace as the antioxidant additive in the paving, asphalt paving material, and also the recycling agent in the asphalt paving material, which is based on the fact of the olive pomace. So look at the olive pomace. Again, it includes the pulp and also the stone. Well, in this study, as I mentioned, so I used the dry olive pomace as an additive. Well, for the olive pomace, the first fact is it is rich in lignin phenolic groups. For example, the Revero test the stone-rich friction in the oleopomace contains about 42 to 44% of the lignin, while the pulp-rich friction contains about 43 to 45% lignin. While the lignin can be used as an antioxidant additive because the lignin can work as a free radicals scavenger. So while there are some like agriculture-based lignin has been used as an antioxidant additive, for example, the rice husk. So based on this fact, we thought probably the oleopomace can be used as an antioxidant additive to retard the aging of the asphalt pavement. And then we will test it. I will show you in the result. The second effect of the oleopomace, especially the oleopomace I use, it has a certain amount of the residual oil even after the olive oil extraction. So for the olive oil manufacturer, so they cannot 100% extract the olive oil. So there is a certain amount of the residual oil in the oleopomace. So we tested in the stone-rich friction. It has about 8.6% of the residual oil. And in the pulp-rich friction, it has about like a 13.7% residual oil, which has a higher residual oil content than the stone-rich friction. Well, for the bio-based oil, it has been used as a recycling agent, for example, the whistle cooking oil, to recycle the, or to be used as a softener or rejuvenator together with asphalt mixture with reclaimed asphalt pavement with a wrap. So we thought this residue oil in the oleopomace can be used as a softener or rejuvenator to include more wrap. So we are going to test these two rationales of this work. So there are three objectives of this work, of this project. The first objective is to explore the laboratory processing method for the oleopomace, and then we can add it in the asphalt binder. The second objective is to assess the antioxidant effectiveness of the oleopomace, especially we tested the asphalt binder to show the antioxidant performance of the oleopomace used in asphalt binders. And the third objective is to evaluate the use of the oleopomace as a recycling agent for the mixture with 25% wrap. Here is the experimental plan. First, we collected the raw oleopomace from the California olive ranch, and then I dry it in the oven at the temperature of 110 degrees Celsius for 24 hours, and then grind it using the coffee grinder into the powder material, and then fractionate the processed oleopomace using the mechanical shaking, mechanical sieving into the small friction that is a pulp-rich friction, which is less than 0.3 millimeter in terms of the size. The stone-rich friction has a large size higher than the 0.3 millimeter. In this project, we did evaluate both and also the together on the effect of the we did evaluate the both the pulp-rich friction and the stone-rich friction to modify the asphalt binders. While in this presentation, I will just focus on the pulp-rich friction because it has a higher lignin content and also it has a higher residual oil in the pulp-rich friction. So in this work, we add 5%, 15%, and 25% of the pulp-rich friction in the asphalt binder and compare with the control binder. And long-term aging was conducted using the 20-hour, 40 hours, and the 60-hour pressure agent visual test, and then run the dynamic shear rheometer test to run the frequency sweep, and also from the frequency sweep test, we determine the glower roller parameter, which is the indicator for the oxidation-induced cracking. And also we run the short-term aging for these binders, and also test the frequency sweep, as well as evaluate the rotting resistance and also the rotational viscosity to determine the production temperature of the pomace modified asphalt binder. Based on the binder test, we select the best performed pomace modified asphalt, and then we design the asphalt mixture with a pomace modified binder with and without wrap, and then we run the performance test of the control mix and also the pomace modified asphalt mixture to evaluate the cracking resistance after the short-term agent and the long-term agent by using the ideal CT test, and also evaluate the rotting resistance by using the Hamburger wheel track test. Well, let's look at the result in terms of the binder result. Again, we want to validate if the olive pomace can be used as an antioxidant agent in the paving material. Again, here we just focused on the GR parameter, which indicates the resistance to the oxidation-induced cracking. Well, look at the GR parameter for the control binder before stirring and after stirring by using the high shear mixture for 85 minutes. For the control binder, just this stirring at 85 minutes, it will cause the aging of the control binder, the GR parameter increase from 270 to 349. Well, for the pomace modified asphalt binder, when we add the pomace in the asphalt binder after the mixing, so actually the GR parameter is lower, so that means it has a better oxidation induced, better resistance to the oxidation induced cracking. Similarly, we see after the short-term agent by using the rolling thin film oven test, so the pomace modified asphalt binder has a better resistance to the cracking. Well, look at the long-term agent for the control binder, especially if we focus on the 40-hour PAV agent and the 60-hour PAV agent. For the control binder after 40-hour PAV agent, the control binder, the GR parameter of the control binder exceed the threshold of the initial cracking damage. And after the 60-hour PAV aging, so the control binder exceed the threshold of the severe cracking damage. Well, look at the 5% pomace modified asphalt binder. So it barely touched the threshold of the initial cracking damage and the severe cracking damage. And when we add more olive pomace in the asphalt, 15% or 25%, so we can see it has a much better resistance to the oxidation-induced cracking damage. Well, here, based on this chart, so I kind of like calculate how many PAV hours for each type of the binder to experience the initial cracking damage and severe cracking damage. So for the control binder, it only needs 37.8 hours PAV hours and 56.2 PAV hours to experience the initial cracking damage and the severe cracking damage. Well, for the pomace modified asphalt binder, so we can see it requires a longer PAV hour to have the binder experience the initial cracking damage and the severe cracking damage. So in this way, I calculate the percent time extension for the pomace modified asphalt binder to experience the initial cracking damage and the severe cracking damage. So just to look at the 15% pomace modified asphalt binder, so it has about 25% time extension to experience the oxidation-induced cracking than the control binder, while for the 25% pomace modified asphalt binder, so it has about 45% time extension. While look at the rotting resistance after the short-term agent, so even though here we see as we include more pomace in the asphalt binder, so the critical high temperature decrease, but all of these tested binder can be classified as a high performance grade of 64. So I would see the pomace modified asphalt binder has comparable rotting resistance than the with the control binder, and also from the mixture test we can verify this. In terms of the workability, I run the rotational viscosity test and determine the production temperature in terms of the mixing temperature and the compaction temperature. By adding 5% oleopomace in the asphalt binder, it has a very minimal effect on the production temperature. When I add 15% pomace in the binder, so the production temperature increase slightly, a little bit, but when we introduce 25% pomace, we can see the production temperature increase a lot. That's because we introduce a large amount of the powder material in the asphalt, so that's increased the production temperature. Actually, based on this, a quick summary of the binder results. What we thought in this project is 15% pulp-rich friction is optimum amount, optimum dosage when we use to modify the asphalt binder, since it has a best performance. First, it has about like a 25% time extension to experience the oxidation-induced cracking, and also it has a similar rotting resistance and the production temperature than with the control binder. Then the second part of this project, we run the mixture test, and we design in this project we designed 3 mixtures, control mixture using the virgin aggregate and the virgin binder. The second mixture, that is a mixture just to use the pomace modified binder, and the third mixture that is a 25% wrap mixture with 25% wrap and the pomace modified asphalt binder. So look at this the first two. After the short-term aging at 60 degrees Celsius for 16 hours and the long-term aging 85 degrees Celsius for 5 days on the loose mix, the pomace modified binder for this mixture, it has a higher CT index, especially after the long-term agent. So it has a higher, almost double CT index than the control mix. And when we have the wrap, 25% wrap in the mix after the short-term agent, it has a lower CT index than the control mix. But after the long-term agent, it has a better cracking resistance when we have the wrap as well as the pomace modified asphalt binder in the mix. Well, look at the additive strength, indirect tensile strength. So it shall be mentioned, if we just use the pomace modified binder in the mix, so it has a lower additive strength, actually, which is lower than 100 psi, which is specified for Caltrans. So the design mixture should have a dry additive strength higher than 100 psi or 690 kilopascal. So we can see here again, the pomace can soften the binder, but we should be cautious, like the pomace may over soften the binder and use it in the mixture. While the joint use of the pomace modified asphalt binder and 25% wrap, so it has a better or higher additive strength. While after the long-term agent, so the 25% wrap has a lower additive strength than the control mix. So that means the pomace did work as an antioxidant additive in the paving material. We run the writing performance using the hamburger wheel tracking test, and by comparing the control mix and the pomace modified mix with the pomace modified binder, so they have the similar writing depths. So here the pomace, oleopomace cannot improve or compromise the writing resistance. While we did observe the severe moisture damage in the control mix and mix with pomace modified binder, so the oleopomace cannot improve the moisture resistance as well either. So while when we use the 25% wrap in the mix together with the pomace modified asphalt binder, so it has a better writing resistance than the control mix and mixed with the pomace modified binder only. So here a quick summary or takeaway from the mixture test compared with control mix. The mixture with 25% wrap as well as a pomace modified asphalt binder has better rotting resistance after the short-term aging from here, and also has a better cracking resistance after the long-term aging. So we recommend to use the wrap and the pomace modified asphalt together. So some conclusions from this study, we can see the processed olive pomace could work as a biorenewable antioxidant and recycling agent in the asphalt paving materials, and the pomace modified asphalt binder and mixture had better cracking resistance and antioxidant performance than the control binder and the mixture respectively. While here we recommend to use the wrap together with the pomace modified asphalt binder because it gives the best performance, and the combined use of the olive pomace and the wrap can benefit the waste management for both olive oil industry as well as the asphalt paving industry. Well, the next phase of this study, we are going to investigate the fundamentals of the antioxidant mechanisms of using the olive pomace. So what kind of ingredients in the olive pomace did work as an antioxidant additive as well as the softener. So in this way, so we can purify or refine the olive pomace and improve the antioxidant and the rejuvenating capability of the olive pomace in the asphalt paving materials. So with that, thank you so much for your listening. Here's my email address. If you are interested in this work, if you have any questions, please feel free to send me the email. And also, if you search the olive pomace in the Olive Oil Commission of California, so here is a report with detailed result and the discussion from this study. Again, thank you so much for your attention.